Now it is recorded. Okay. So if there is a strong acid and a strong base, then you get a neutral salt. So one full class was there on this topic. Neutral salt means pH is controlled by water and pH is 7. Means at the equivalence point pH is 7 for a neutral salt. So we discussed these type of titration curves in the last class, and we did one question on titration like this one. This is a strong acid with strong base, and you can see the pH at the equivalence point is 7. pH at the equivalence point is 7. It's a strong acid with strong base. Salt is neutral. Right? Okay. Now, if the acid is, I'm still getting the noise, Venki. Give me 1 second, children. I'm trying to adjust something. Okay. So this is the case of a strong acid and strong base where the salt is neutral. But if you take a weak acid with strong base, can you see the pH at the equivalence point? pH at the equivalence point is basic. And I gave you the reason also, because the conjugate of this weak acid, what's the conjugate of this weak acid, children? CH3COO minus. Is a strong conjugate base. It is stronger than water. So at this equivalence point, you have only this salt. Acid is 0, base is 0. So this salt is there. So the salt is going to control the pH, right? Okay, Yusuf is not there. Yusuf and Partha are not there. Now, this is a strong conjugate base is going to react with water to give you CH3, COH and OH minus. This OH minus will make the pH at the equivalence point more than 7. Sanvi, is it okay? So a weak acid with strong base will give you basic salt. Basic. This is a basic salt. pH is controlled by, here the pH is controlled by CH3COO minus. The conjugate base, CB means conjugate, of this weak acid. WA means weak acid. This conjugate is stronger. Weak acids, they give us strong conjugate base. And that's the one which is going to react with water at the equivalence point to give you OH minus. Then if the titration is of a strong acid with weak base, then the salt is, this salt, you can check the pH at the equivalence point is 5.28. You can see this. So what's the nature of the salt? Yes, Atharva? If the pH is 5.28 at the equivalence point, pH is less than 7. See this one. So what's the nature of the salt? Salt is not neutral. So what is it? Acidic, basic or neutral? It's not neutral, but what is it? Acidic or basic? Acidic. Athava acidic, pH is less than 7. Less than 7. Acidic, right? Okay, so that's the nature of the salts which I discussed in the last class. So, and I discussed one of the titration calculations for this particular question. I was checking the video. No, the chart is showing you the pH at the different intervals of titration. You have to watch the video of the last class. You're doing titration, you're adding base into the acid or acid into the base. You can see here titration curve. This is the titration curve. Today my aim is to make you understand this titration curve. See here the volume of HCl added. Here is the pH of the solution in which ammonia is there. Ammonia is a base. So at this point, what is the volume of HCl added? Answer this question. At this point, what is the volume of HCl added? Yes, 0. The volume of HCl added is 0. If the volume of HCl added is 0, then it means pH is controlled by ammonia only. That's why the pH is so high, because it's a basic solution, right? And as you start adding HCl, ammonia is reacting with HCl to give you ammonium chloride. So initially, till the time ammonia is there, when all the ammonia is neutralized, then this is the equivalence point, when all the ammonia is neutralized. So to reach the equivalence point, you are adding HCl. This is the point at which all the ammonia is neutralized. There is no more ammonia. Ammonia is 0. HCl is also 0. Both of them are 0, 0. So what is there at the equivalence point? Only ammonium chloride, the salt. What is here in this area? What is here, children? In excess? Ammonia. Ammonia is in excess. What is here? Here, the excess of HCl. That's why the pH is so low. So here you have ammonia in excess. Here you have HCl in excess. Here you have only ammonium chloride and water. So this is something which I'm going to discuss again. I discussed this in the last class also, but we'll do it again. Okay, ready? So this is the graph which we did, and we made the graph. So I'm making the titration curve here for this one. Here is the pH. Here is the volume of, read the question carefully. What are you adding? This is the amount of BaOH twice in the conical flask. What are you adding? This is BaOH twice. How much? 80 ml, 0.1 molar. And from the burette, you were adding HCl. See, read this language. This is HCl added. And we did this complete question. I calculated pH at the different levels, right? Now, the titration curve which we made at that time was this. The pH meter is embedded here. This is the pH meter. So the curve was like this. Like this. And this is the equivalence point which was at the pH 7. Now I'm going to show you different points. This point, this one, is when the volume of HCl added is 0, A point. Here the pH is controlled by only this initial concentration of BaOH twice. No one else is there. So you just, it's a strong base, very strong base. You just write on the dissociation of this strong base, calculate the concentration of OH minus. So the concentration of OH minus From this BaOH twice will control the pH, and pH is very high, somewhere around 12. We did the calculation. And then up to here, the pH is still very high. The graph is slightly like this, not like this, the way I made earlier. It's like this, like this. Okay, now there is a slight decrease in pH because still up to here, up to this volume, your BaOH twice is in excess. So all this area, all these pHs are controlled by BaOH twice, which is very strong base because it is in excess. You can see the calculations in the last class. But once you have reached at this point, this is the equivalence point, 40 ml. I'm not discussing this in detail because we did it in the last class. So I'm asking you to refer the last calculations. At this point, the pH was this because this is equivalence point. Here the pH is controlled by water because it's a strong base with strong acid. Strong base and strong acid will not give you very strong conjugates. So who is stronger there at the time of equivalence? Water. And what's the pH of water? 7. And after this, what is in excess? The hydrochloric acid. After equivalence point, you are still adding hydrochloric acid. So hydrochloric acid is in excess here. And the pH is determined by the excess of H plus ions. This E point. pH is totally controlled by HCl. D point, pH is controlled by water. All these points, pH is controlled by strong base BaOH twice. So they will give you a curve like this. And they will say, okay, the equivalence point pH is 7. Identify the acid and base. They are strong or weak? Answer is both of them are strong. It's a strong acid with strong base. That's why pH is 7 at the equivalence point. Then they will keep asking question like this. How to determine the pH at this point? So you will say the strong base, whatever base is there. If the graph is like this, then it is strong base. But the graph can be like this also. Like this. Then this is the strong acid. This is the equivalence point, and this is the strong base. So then they may ask you that how to determine the pH at this point? The strong acid, initial. How to determine the pH? The excess of strong acid left and calculating the new concentration. How to determine the pH? Water. How to determine the pH here? The excess of base. So that's the review of what we did in the last class, right? Now today we are going to do titration curve of a weak acid with strong base. All carbon containing acids are weak acid. So let's make the picture of the titration setup. So there is a burette. In the burette, you have to take one acid or base. There is a stand for the burette like this. And then there is a conical flask here. Conical flask. Conical flask is going to contain one of the acid or base like this. Okay. Okay. Now read the question. 100 ml of 0.2 molar acetic acid. Answer my question, children, now. So where is acetic acid? In the burette or in the conical flask? And is titrated by 0.1 molar KOH. Acetic acid is carbon containing acid HC2H3O2. And the strong base is KOH. You are adding volumes of KOH being added. Whatever you are adding will go in the burette or conical flask. This is the burette. Burette. This is the burette. Yes. So your KOH is in the burette. Who is this? Sammy, very good. KOH is here. And what is here? Acetic acid. We need an indicator also. That will show you a color change with the change in pH. When the pH goes from acidic condition to basic condition, indicators, they change their color. Okay, so let's start the titration. So first, before you start the titration, you have to understand that the volumes are changing. You started with here, what is the volume of this acetic acid? 100 ml? 100 ml, right? And concentration is 0.2 molar. So when you are adding this KOH from the burette into this conical flask, the volumes are changing. As the volume changes, molarity changes. So don't work in molarity term here because molarity is continuously changing at every point of the titration. So we will work with millimoles, moles and millimoles. It's better to work with millimoles because volumes are given in milliliter. You remember this equation that molarity equals to millimoles over volume in milliliter. So millimoles I can calculate by using this equation that it is molarity times volume, this equation. So all these things we have done. Children, you are not doing any quizzes on the website. I would like to share the result with your parents. The reason is because now this is vacation time. If you are not still doing, then you'll be wasting your time. Okay? It's better you start doing them. Quizzes. So please don't mind. I'll share all the results with the parents by the end of this week. And then we have to think about it. It's not a complaint. You see, now we can think, parents, and I have to decide that how to make you comfortable with the quizzes. So you have to do the quizzes during this break. Okay, so children, we are okay with the setup. We are ready for the titration calculations. So we are going to carry out a chemical reaction of an acid with a base. What's the product here? What's the product? Write on the product, acid-base reaction. You will get the salt of the weak acid plus water. That's the reaction, right? Yes, good. I'm going to erase everything after showing you this complete setup. Partha, you're there in the class? Partha. Okay, Partha, can you inform Yusuf? Sorry for telling you all these things. Can you send a message? Thank you, Partha. K plus C2H3O2 minus plus H2O. Children, do not miss classes. We are left with only one unit, and that unit will go very fast because it's a very simple unit. And you have already done few things earlier, and that will be the last unit. And very important, very easy. Okay, so this is the reaction. As I said that we are going to work in millimoles, and millimoles equals to millimoles are molarity times volume, right? So let's work for the A point. At the A point, what is there? KOH is 0, A point. KOH is 0, right? See, 0 volume. Yes. So what is there? Only this acid. You have not added any volume. You have not added any volume. Will there be any change in the concentration of this acetic acid? Will there be any change at the A point? No, because volumes are, there is no change in the volume. So there is no change in the molarity. And it's a weak acid. HC2H3O2 is a weak acid, right? And weak acids, they are going to dissociate partially. For the weak acid, if I want to determine the pH at the A point, I need to make the rise table. Do you remember how to determine the pH of weak acids? So the pH of this weak acid, this is just A point is just weak acid, nothing else is there. So I'll determine the pH by making the rise table because weak acids are not fully dissociated. This is the reaction, initial, change, equilibrium. Remember children, rise tables are always in concentrations. So now can you complete the table, Sanvi? Can you complete the table? So what's the initial concentration here? No, no, no. Zero. Why 0? Acetic acid, 0.2 molar. 0.2 molar, right? How much H plus? Yeah, 0.200. You have to take care of 3 significant figures here. And H plus is initially 0, 0. Right? Now change. Remember how to write the change? Minus X plus X plus X. Equilibrium 0.200 minus X, X and X. Ka, you remember Ka, the dissociation constant of the acid, is the concentration of H plus times concentration of C2H3O2 minus divided by concentration of HC2H3O2. Plug in the values. X squared over 0.200 minus X. Very good. Which is equal to the Ka value given to you here. 1.8 times 10 raised to power minus 5. Can you do approximation? Can I assume this minus X negligible? Yes, because Ka is very small. You just compare the initial concentration with this Ka. You can see the difference is very large. So it means X is negligible. So I can approximate it like X square divided by 0.200 as 1.8 times 10 raised to the minus 5. Get the value of X. Get the value of X, children. Who is doing calculation? It will be 1.8 times 10 raised to a minus 5 times 0.200 square root. This is how we worked many questions earlier also. How to determine the pH of weak acids. And how much is this? You did the calculations? Sanvi is saying X is 0.002. Is it right, children? Please do the calculation. Anyone else doing the calculation? Semi? You have to go for 3 significant figures. So I think Sanvi is right. If I go for 3 significant figures, I have to drop 7. No, then it is 1 point. Yeah. It is 1.90 times 10 raised to power minus 3 units molar. Yes, yes. Atharva, you're right. Okay. Jyoti is here. Okay, I was sending her messages. Jyoti, why you joined the class late? It's very important, Jyoti. You're a good student. Okay. These things will trouble you during AP exam. So last 2 topics are very important. Okay, so this unit is molarity, right? Now, what is this X? X is H plus ions concentration. See here. What is X? X is H plus ions. So X is nothing but the concentration of H plus, which is 1.90 times 10 raised to power minus 3 molar. So get the pH. pH will be, I gave you a trick also, otherwise you can plug in this value, or you can do like this. 10 raised to minus 3, you take negative log, it is 3. 3 minus log. Atharva, see this shortcut? Atharva, Semi. Boys are more interested in the shortcuts. See? This 10 raised to minus 3 can be taken as 3. Negative log of 10 raised to minus 3 is 3. 3 minus log 1.90, how much? And the answer should have 3 significant figures. Means after decimal. After decimal, you should have. Oh, you joined only 3 minutes late. Okay, I didn't see you then. Maybe you just started answering. Okay, what's the answer here? Sanvi, Jyoti, what's the answer? After decimal, go for 3 significant figures. In pH, first number is not counted. Before decimal numbers are not counted for sig fig because they are exponentials. Waiting for the answer. It is 2.721. So you people are not answering anything? Not doing calculations with me? Is this the pH? Check my calculations. Okay, okay, good. So when we didn't add any base, so how to determine the pH? pH is determined by making rise table for weak acid because only that weak acid is controlling the pH. And we calculated the pH, so I'm going to erase this because I need space. So at the A point, pH is controlled by weak acid rise table. We are going to make the rise table and the pH was 2.7212, right? 2.7212 at the A point. Okay, so I erased everything because I need space, but I hope you have understood that at the A point, it's just the weak acid, make the rise table, use this Ka value and get the pH. But at the B point, reaction has started. So my acid is O2, this is weak acid, and KOH, giving me the salt and H2O, right? NH2O. That's the reaction. Now pay attention because you have started adding base into it. Titration has started. Atharva, if you have not watched the last video, then pay attention. I'm teaching the same thing. Titration has started. Now this is the reaction. Now once the titration has started, you are changing the volume now. What is the volume now? How much volume was there of the acid? 100. In 100, how much KOH added? 50. Volume has changed. So you have to work with millimoles now. Millimoles. Initial and final. Because concentrations are changing, molarity is changing. Molarity is changing because volume is changing. So it's better to work with millimoles. So initially, how many millimoles of acetic acid? Please start answering now. Millimoles. You remember millimoles? How to calculate millimoles? Is molarity times volume in milliliter. So molarity and volume given, Sami. So how many millimoles of this initially before titration? Yes, children, do it fast. Isn't it 20? Am I right? 20.0. Multiply these two numbers. Okay, and how many millimoles of KOH initially before titration started? You added 50 ml of KOH with 0.1 molar KOH. So what is it, children? Point, not point. Multiply these two. Isn't it 5.0? You're not doing calculations. This is initial. Understand this. Initial means there are 20 millimoles of acetic acid in the conical flask, and we have added 5 millimoles of KOH. We are just adding it. Okay. Reaction has not started. So initially, is there any amount of this? No. Reaction has not started yet. Is there any water? So water as it is, we are not interested. Okay. Because here water is not playing any role. It's just the spectator. So 0, 0. Yes. Sami is right. Now let's see here. Finally, now which one is the limiting reactant? They are reacting 1:1. Answer my question. Which one is the limiting reactant? The acid or the base? See, they are reacting 1:1. After the reaction, which one is left and which one is used up completely? Mhm. Yes. Any one of you? Jyoti? Sanvi? 1:1. 5 will react with how many acetic acid? 5 millimoles will react with how many? Will react only with 5, but they are 20. So how much is left? 15. How much KOH is left? 0. So who is the limiting reactant? Who is the limiting reactant? Please type here, all of you. Who is the limiting reactant? Limiting reactant is KOH. Remember that. Now the titration has started. There is plenty of acetic acid. You are adding KOH from the burette, and initially at this point B, limiting reactant is still acetic acid. And how much this is formed? Yes, complete it. Now this is not 0. How much is this? 5. Right? It's 1:1:1. How much water? That we are not interested, but you can write 5, right? Here you can write 0. No problem. But water is not going to do anything here. Okay, so that's the situation after titration. After titration, in that conical flask, we have 15 of this and 5 of this. This is a weak acid and this is its conjugate. Right? Weak acid with its conjugate. What is it? A buffer. How to determine the pH? Now buffer is made. See? Because there is no strong base. Strong base is 0. So the solution is just a weak acid with its conjugate. So it's a buffer. For the buffer, you can use Henderson equation to know the pH. Don't make rice table. So pH equals to pKa. You remember Henderson equation? Logarithm concentration of C2H3O2 minus over concentration of HC2 H3O2. This was the Henderson equation. Do you remember that? This is for the acid. Do you know pK? Yes, K is given to me. So what is pK, children? What's the pK? Negative log of Ka. That is 1.8 times 10 raised to power minus 5 plus log. What's the concentration of this acetic acid? Concentration. Concentration means molarity divided by volume. Sorry, concentration means moles divided by volume. But here we are working with millimoles. So it is 15 millimoles. I'm working out the concentration of acetic acid. Concentration square bracket is 15 millimoles divided by the total volume. What's the total volume at this point? Atharva typed it earlier. He said the total volume is 150. Why? 100 plus 50, 150. 15 millimoles divided by 150 ml. That's the concentration of your acetic acid. What's the concentration of acetate? Can you work out, children? Don't do calculations. Leave it like this. I want to show you something. What's the concentration of acetate? Isn't it millimoles of acetate, which is 5 divided by 150, same volume? 5 millimoles divided by 150 ml. So children, I'm saying don't do calculation because I want to show you here that the volume is same. This volume and this volume. Can I change this equation? Can I write it as millimoles of C2H3O2 minus over millimoles or moles? Right now we are working with millimoles, but maybe in some questions you'll be working with moles. So it's just the ratio of their moles in the solution. Do you agree with that? Is this modification of the equation is okay? Because volume is same, 150. When you plug in these value, this and this, when you take the ratio, 150, 150 cancelled out. Isn't it, children? Is this clear? I modified the equation, right? So how much is this? Did you check the pKa, children? It must be somewhere around 4.74, and it is. I'll take only two significant figure. 4 is not counted in sig fig. So only this means this number has two sig fig because this is pKa. Don't count 4. It's exponential, this exponential. Right? Plus log. Now how many millimoles of this acetate? 5. How many of acetic acid? 15. This number is greater than 1 or less than 1? It's less than 1. This complete answer will be less than, is negative. This complete answer is negative. So answer is, no one is doing calculation? Sanvi, are you having problem in understanding this concept? If you start asking, you will feel better. Ask any type of question. Don't worry about stupid or silly. Don't worry about it. I'm getting 4.26. These two numbers. Yes, Jyoti. Okay, so what I'm trying to say that when this ratio, write down, this is a very important point. When the millimoles of conjugate means the salt, like here this is conjugate base, is more than millimoles of the weak acid, then pH of the buffer is always greater than pKa. Because in that case, ratio is more than 1. This answer will be positive and pH will be more than pK. And if this is one situation, second situation, if millimoles of conjugate base are less than millimoles of the weak acid, then in that case pH is less than pKa, because then in that case this ratio is less than 1. Logarithm of less than 1 is negative, and this complete answer, this negative means this plus will become minus and your answer will be less than pKa. Are we clear about it? So please write down these two lines in your notes. If you write down, then you will see that you can answer many multiple choice questions on buffers very fast if you understand and practice it. So what is the pH at the B point? 4.26. We calculated here 4.26, right? So after addition of small amount of that strong base, and strong base is the limiting reactant, your solution is now a buffer. And now you have to check the pH of that solution by using Henderson equation because it's a buffer. You need not to make the rice table. You can make a rice table. You can calculate using a rice table, but that will be more difficult. It's rather using this Henderson equation where you can take the ratio of the millimoles. I changed the equation here. I told you why. I explained you why. Okay. Now I'm going to erase this part to create more space. So we are done with the B part, right? B part is done. Can we do this C part? So children, can you help me in the C part? One second. I have to erase this. Okay. We are on the C part of the titration. C part here. Ready? So in the C part, how much acetic acid? Still the same. Same, the one which is there here. Same, right? So it's still 20. No change. How much KOH? Millimoles of KOH in the C part. Start helping me. How much KOH? You have added 100 ml. 100. So how much KOH? 100 times. Yes, children? This is the molarity. 100 times zero point 0.1. So how much? 10. This time it is 10. Molarity times volume, millimoles. We are working with millimoles in this reaction, initial, final. So there are 10 millimoles of KOH, right? Right? Okay. Now complete this next table. This was 20 and this is 10. Can you complete the table? No one is helping me. So after reaction, how much this is left? Who is the limiting reactant? How much KOH left? How much acetic acid? How much sodium, this potassium acetate formed? Completed. They are reacting 1:1. I've already given you their initial millimoles. Initial millimoles of the acetic acid is 20. KOH is 10. Can you work out, Jyoti? Sanvi, Atharva? KOH is still limiting. She is right. It's 0. But how much acetic acid? Sanvi is right. 10. How much potassium acetate? Semi? Yeah, good. Semi good. Partha, your answers are not coming. How much potassium acetate? 10. Yes, 10. Now, this is 10 also, but we are not interested. Now, who is going to determine the pH? What is it? The pH is controlled by the acetic acid and the acetate, both of them. It's a buffer solution. You have both of them. It's a buffer solution. Use Henderson equation, the same one which I was using earlier, right? So 4.74 plus log. Now you're going to plug in this ratio, 10 over 10. There is no need of calculating concentration because volume is same. What's the volume at this point, children? What's the volume of the solution at the C point? Any one of you? Volume of the solution at the C point. Mhm. In 100 ml of acetic acid, you have added 100 ml of the base. So Atharva is right. Total volume is 200 ml. And that is same for both of them. And that cancelled out. So don't worry about the volume here. But now this is the best buffer. Best buffer. This point is the best buffer. What is best buffer? Which I have done earlier also with you. When the pH is equal to pKa. That is the best buffer. Write on this point, please. It's very important point. Best buffer. pH equals to pKa. Why? Because log 10 over 10, log 1 is 0. So what is the pH here? It's nothing but pKa. And what's the pKa value? This one. So when can I see the best buffer of the solution? When the solution can behave like best buffer? When the pH is equal to pKa. And buffer capacity? Buffer capacity is that it is the every buffer has a limit of controlling the pH, and that is the pKa value plus minus 1. Means your buffer is going to behave like a buffer. It can control the pH only when the pH of the solution is in this range. If it is equal to pKa, best buffer. If they are equal, best buffer. But it can control the pH up to +1 and -1 around the pKa. These are questions from the titration curve. So what's the pH at the C point, children? What's the pH? Is 4.74. Can you see that hardly any change in the pH? 4.26, 4.74. Hardly any change. This is buffer area. Ready for the D part? Sami, can you answer the D part now? In the D part, how many millimoles of acetic acid? Still the same. Same, right? How many millimoles of KOH? Can you work out the millimoles of KOH now, children? How many millimoles? Yes, 15. 15. So I'm making it slightly big so that you can see the changes. We are doing the D part now, D. Okay, we are going to work out the pH for the D part. Remember the best buffer, okay? So I'm just erasing everything. I need some space to write here. So we are working with the D part. Who is the limiting reactant? Who is the limiting reactant? Still KOH, right? How much acetic acid left? 5. How much this potassium acetate formed? 15. Reaction is 1:1, right? You will decide the amount of potassium acetate from the limiting reactant. 15 will give you 15. 10 will give you 10, like this. So is it a buffer? Yes. You have a weak acid with its conjugate base. And KOH is 0, limiting your strong base is not there. So what's the pH? I will use Henderson, right? So pH at the D point is equal to pKa plus log millimoles of the conjugate base. Millimoles of conjugate base over millimoles of weak acid. Remember, I changed the equation. If you have problem with the equation, you don't want to change it, it's okay. But you know that volumes are same for both of them. They are in the same volume. What's the total volume at the D point, children? Total volume of the solution at D point is 100 plus 150, 250 ml, right? Plug in the values. What is pKa? You remember we calculated 4.74. It's still the same. Plus log conjugate base. How much? 15. Weak acid. How much? 5. This ratio is greater than 1, right? If it is greater than 1, then pH will be greater than pKa. You can calculate. So what's the pH? 5.22. That's the pH. You are not doing calculation. Hello? Yeah. Okay. Sanvi is saying 5.4. Okay, Sanvi, check your calculations again. Okay, so that's the pH at the D point is 5.22. Atharva, Sami, Partha. Partha, I'm not getting answers from you. Are you busy in something? Partha, no answers from you at all. Then why you are not answering? You are not doing calculations. You are not answering any calculations. Partha, you have to interact here, okay? At least start doing calculation. If points are not clear, at least participate in calculation so that something should be clear to you. At least calculation should be clear to you. You must learn something in this class. Okay, now let's see the E part. We are working with the E part. E part. So I'm writing the pH. I have written all the pH. pH of the A by using the Rice table of the weak acid. B, buffer equation. C, buffer equation. D, buffer equation. E. Let's see at the E part. Do the changes for the E part, children. Ready? So what are the millimoles of the weak acid? Millimoles of the weak acids. Still the same, 20, right? What are the millimoles of KOH? You see, every time they are starting with this solution. For the A also, B also, C also. Acetic acid is this much. And then they are adding that much volume into this volume, into that solution. How much KOH? And Sanvi is saying 20. This semi 0, 0, right? Now, can you work out the who is the limiting reactant? No limiting. What does it mean? That this is also 0, this is also 0 after the reaction means equivalence point. This is the equivalence point, children. This point is equivalence point. And here, what are you getting? How much acetate you are getting? 20. And water is also 20. Semi, you are there? Now, who is going to control the pH? Is it a buffer? Is this a buffer? Do you have the weak acid with this conjugate? No, it's not a buffer. So don't use Henderson equation at the E point. At the E point, we have to use, who is going to control the pH, children, at the E point? Who is going to control the pH? This conjugate, this one, this is stronger than water. But I cannot use Henderson equation. So I have to see the reaction of this conjugate base with water, and I have to make the rice stable because it's a weak base. It is weak, but it is stronger than water. Stronger than water, right? No, Sanvi, this is stronger than water. It's a strong conjugate base of a weak acid. It's not as strong as KOH. It's not fully dissociated. It's still very weak, but stronger than water. So in the water, it's going to behave like a base, right? So it's behaving like a base. It's taking away hydrogen from water and generating OH minus. These are the definitions of the bases. Arrhenius definition, Bronsted-Lowry definition. All the definitions are valid here, right? We did all these things earlier. But now I have to make the rice table. For the rice table, I need the concentration. So what is the concentration of your acid, this weak base? The concentration is defined as molarity. It is millimoles divided by volume in milliliter. How many millimoles? 20. How much is the total volume at the E point, children? Total volume at the E point. Type the volume. We are at the E point of the titration. How much is the total volume of the solution now? You started with 100 of acid and you added 200. So the total volume is 300. So what's the molarity of this solution? Type the molarity of the solution. You're doing calculations. It is 0.067. If I go for two significant figures, I have to go for three significant figures, 667. So 0.0667 molar. Right? Yes, Partha. Good. Go for three significant figures, Partha. Okay. Now, initially, this is rice table. Now I'm working with the molarity. I cannot work with the millimoles in the rice table. Remember that. So you need molarity. So I calculated molarity. Now this is 0, 0 rice table, the way we were making earlier. And this is 0.0667 minus x, x, x. What is this equation represents? This equation represents the dissociation of a base. So it means I need Kb. This is the rice table for Kb. And Kb is equal to the concentration of this times this divided by this equilibrium concentration. So that is x squared over 0.0667 minus x. But where is Kb? Is it given to us? No. How to know Kb? Do you remember this equation, children? Ka times Kb is any one of you? Kw. So what is Kb? For the conjugate acid-base pair. These are conjugate acid-base. This is the acid and this is the conjugate. I know Ka is given in the question. So K is given to me. And Kw is 1.0 times 10 raised to power minus 14. And what is Ka? That's given. So it means I know Kb. What is Kb? Kw divided by Ka. And this value I think is very low. Is it 5.56 times 10 raised to a minus 10? I'm just recalling from my memory. Can you do it, children? Can you check? Kb. Can you check Kb, children? Sammy? Anyone doing? Check this value of Kb. Is it right from this calculation? Sanvi, Jyoti, is it right? Partha, Atharva, please don't halt the class. Can you confirm the value? Atharva, can you confirm? Because I don't know whether you are doing the calculation. It should not take so much time. Okay, thank you very much, Sanvi. And you're getting what you are getting. You are not with me. I'm asking you to calculate Kb, and you are calculating the concentration. This one that we have done earlier. This part we have done. I'm asking you to calculate Kb, not this concentration. That is already done. Atharva, please stay with me in the class, okay? What calculation you are giving me? You are giving me this. Right now I'm asking Kb. Please focus on the point which I'm discussing. So we are here, Atharva. We are here. So we have x squared. Can I do approximation, children? What's the value of Kb I got? I'm writing it big here so that you can see. There are so many calculations going on. So I'm writing big here. So Kb is 5.56 times 10 raised to a minus 10. No units. Equilibrium constant, no units. So my question is, can I do approximation? Is this Kb very large, very small? This Kb is very large or very small? Mhm. Is very small. So you can do approximation. What does it mean? It means that x squared divided by this 0.00667 minus x. This x can be ignored. So x squared divided by 0.0667 is equal to that value of Kb, 5.56 times 10 raised to the power minus 10. Solve for x. All of you are here? All eyes here, right? Atharva, you are here with this calculation? Can you solve for x? Solve for x. Yeah, please, Atharva, solve for x. And what is x? X is OH minus. Jyoti, get the value of x and get the POH. Because x is OH minus, it is not H plus. So x is concentration of OH minus. Get the POH and then get the pH. And that will be the pH at the E point, the equivalence point. Equivalence point pH is controlled by the conjugate base. Doing it, children? So I'm going to give you answer of the pH only. Okay, Atharva. Atharva is giving us the value of X. Get the POH, Atharva. Okay, Jyoti, Atharva, good. Get the POH now. This X is OH minus. X is OH minus. See here we are dealing with the base. It is OH minus X is X in the rice table. So you calculated X and then get the POH and then get the pH. pH then. Atharva, what's the pH? Partha, do this question. Yeah, Partha is doing good. Semi, you know pH plus POH is 14. By doing these questions with me, I'm helping you everywhere. I'm giving you what equation you have to use. So keep using them. I know that you are not doing this in the school. So maybe you're forgetting something. You are not doing anything on the website also. So that's why I keep telling you everything. So start doing them. You will see you will start retaining things. Okay. So pH plus POS. So pH Atharva is saying 8 point. Here the pH is 8 point. This pH is basic or acidic? The pH is basic or acidic? Yeah, it's a basic salt, right? And it's an equivalence point, Sammy. Equivalence point pH is basic. It's not neutral. Means you see here, this is the equivalence point. When the acid and the base are 0, 0, 0, this is the equivalence point. pH is controlled by the conjugate, right? Okay, I'm going to erase this now, this part. Now we are on the F part, the last one, the last of the titration. You make the table again, initial, final. We are doing the last part. We have the pH of every part, A part, B part, C part. We did all the calculation. It's a very big question, but it's going to give you a good review how to calculate pH of the buffer solution, how to calculate pH of a salt, how to calculate pH of weak acid or weak base. It's the review of everything what we have done. And you will see in the review classes, I will do similar type of question again. Review of the AP classes. That will be done in the month of March. Okay. So now how much initial amount? Ready, children? How much initial amount? Still the same. There is no change in the initial amount of the acetic acid. So how much? 20. How much KOH added? 25. 0, 0. Who is the limiting reactant now? We are doing the F part. Who is the limiting reactant? This one. How much KOH left? 5. How much acetate formed? 20. Water? 20. Now, who will control the pH? Whoever is stronger. This answer I'm waiting from you. Who will check who all is there in the solution? There is KOH. There is the conjugate base of the weak acid. It's also basic. And there is water. Who will control the pH? Yes, Sanvi. Very good. KOH. No one else. They are very weak in front of KOH. Semi good. KOH is the big fighter here. So we need to know the concentration of this KOH. Because to know the pH, I need the concentration because it's a strong base. It's going to dissociate completely. K plus and OH minus. I need to know the concentration of OH minus. So what's the concentration of OH minus? It is the millimoles of OH minus divided by total volume. Do you know the millimoles of OH minus? Yes. How much? 5. 5. What's the total volume? 250 plus 100. 350. What's the concentration of the OH minus? Get the POH and get the pH. Can you work this answer faster than me? Get the molarity of OH minus, POH and pH. So the molarity is 0.0143. And if I take the negative log of this answer, I will get the pOH as 1.860. That's the pOH. And if I subtract this number from 14, I will get 12.141. That's the pH. You see, I've done calculation faster than you. I'm teaching also, I'm speaking also, everything I'm doing. And I'm using my calculator, writing on the whiteboard. So how come you could not do it? Children, do plenty of questions so that in the exam you'll be fast. Exam is not just knowing the things. Exam is also doing the thing in less time, doing it accurately in less time. So the examination is testing you for your knowledge and for the speed also. You don't have unlimited time over there. It's not that you start your exam in the morning and you can sit there up to evening. No, every question has a limited time. So don't expect that I'll practice only in the last month. At that time, you have more pressure on yourself because maybe some of you are taking more than one AP. Okay, please practice. Okay, so now what is the pH at the F point? 12 point. Something, I erased it. Tanvi, did you write the pH at the F point, which I calculated? It is 12.141, something like that, right? Okay. Now, let's make the titration curve. Titration curve. What are you adding? Volume of KOH. And you are adding volume of KOH like 50-50 like this. So this is 0, this is 50, this is 100, this is 150, this is 200, and this is 250, like this, 50-50. And here is the pH. So what's the pH at the 0 point? When no KOH is added. You remember we made the rice table? It is 2.721. Somewhere here. 2.721. What's the pH at the 50? 4 point. Somewhere here. What's the pH at the 100? 4.74. All the values are written here, children. I'm just making the titration curve. What's the pH at 150? What's the pH at 200? 200 is the equivalence point. This one. There is a sudden jump. pH is 8. And then more jump. And pH is somewhere at 250. pH is somewhere here. Let's join the points. Like this. This is the titration curve of a weak acid with the strong base. And this is the equivalence point. And the pH at the equivalence point is 8.78. This is the equivalence point. 200. Sorry. 200 is the equivalence point. This one, equivalence point, 200. I'm not using a scale, so that why things are not getting aligned properly. 200 is the equivalence point. What is the half equivalence point, children? When half of the acid is neutralized? Can you give me the volume of half equivalence point? I need 200 ml to neutralize it completely. So how much is needed to neutralize it exactly half? 100. This one. This 100. This one. This is half equivalence point. Remember at this point, pH is equal to pKa. pH equals to pKa, the best buffer is the half equivalence point. Half equivalence point. What's the buffer capacity? Buffer capacity of any buffer is up to this limit. Means the pH can be, pH of the buffer can be +1 higher than pKa or -1 lesser than pKa. In the range of this value of pH, your buffer is going to work like a buffer. If it is more than that or less than that, then it will lose its buffer nature. Then it cannot work like a buffer. Buffer, you know, the one which resists any change in pH. And I told you the buffer action also. Okay, very fast, I'm going to give you a review of this titration. When the volume of base added is 0, I made the rice table. Rice table for the weak acid and I calculated the pH. But after that, this point, okay, I'm highlighting it, children, with a dark color. From here up to here, use Henderson equation. It's a buffer. This area is buffer. And when is the best buffer? Best buffer is half equivalence point. Best buffer. These are the questions from the titration curves. This is best buffer. This one. And then you say weak acid with strong base. So the conjugate salt, the conjugate of the weak acid is stronger than water at the equivalence point. The pH is controlled by conjugate base. So you need rice table again. What is needed? Rice table. For what? For the Kb, you remember Kb equals to Kw divided by Ka. And then you make the rice table for the conjugate base and then check the pOH and then pH. We did all these things. But after equivalence point, your KOH was in excess. And the pH here is controlled by KOH. So get the concentration of OH minus pOH. So that's the meaning of titration curve. One last question on the titration curve without calculation. So I'm expecting you to answer this question very nicely. So this is a question for you children, not for me. I want to start unit 9 also today. So let's do it very fast. Within 5-6 minutes, if we can do this question. This one. Ready? The stoichiometric equivalence point. So in this graph, where can you see the equivalence point? Okay, I'm marking the points just to make you comfortable. Let's say this point, this is A, this point. And this point is B. And this point is C. And this point is D. So I have marked all important points. So A, which point represents the equivalence point? Answer it. Otherwise, very fast and very accurate. Sami, Partha, is he right? That's the equivalence point, right? Equivalence. Yeah. Okay. The reason with maximum buffering, the buffer capacity, you remember, pH equals to pKa plus -1. So which reason is of maximum buffering, best buffering? Very good, Atharva. Jyoti and Sanvi. I hope you're understanding this. Yes, yes. This is the best buffering area. Plus minus 1. You remember pKa, buffer capacity. So in this area is going to work like best buffer. Perfect. Perfect, Atharva. Very good. And C point. So where you have pH equals to pKa, which is also called as half equivalence point, because half of the acid is neutralized. So you have the concentration of the moles or millimoles of the acid and its conjugate equal. So when you use the Henderson equation, pH equals to pKa plus log millimoles of the conjugate over millimoles of the acid. That ratio is 1. So pH equals to pKa. So which point? Atharva, which point? You already know it. The half equivalence point, D. D is pH equals to pK. Yes, Partha, very good. Now let's see the D point. This is the titration I did with you. We made the titration curve and I explained you everything. That's why Atharva is answering very fast. Sanvi, your answers are not coming. Jyoti, Sanvi, I hope you have understood this titration curve. pH depends only on the acid, He. Can you answer this? Only He, rise table of the weak acid. Where? Yes, very good. A, semi A point. At this point, you didn't add any base. See, the base is 0. So who is going to determine the pH? The acid only, right? Now let's see the E point. E point, the acid is 0, the base is 0, and the pH is determined by the, yes, acid is 0, base is 0, nothing is there, only is conjugate. So the answer is B. Very good, Sanvi. Jyoti, your answers are not coming at all. F part. pH depends only on the amount of excess of strong base added. Yeah, that is C. Here in this area, C. So these titration curves are there as multiple choice questions. And that's how they will ask question. They will put some mark on it. They will ask you to identify what's this point. At what point of the titration you have this particular pH. This is very popular concept. pH equals to pKa is half equivalence point when half of the acid is neutralized, right? Okay. Can we draw the titration curve of this? You are titrating a base with a weak acid. No, a weak base with a strong acid. Read the question and let's make it very fast. Titration of a weak base with strong acid means I'm measuring the pH of the weak base. So I start from high pH. This is, and here I'm adding volume of acid. Initially 0. The graph will go like this, children. Like this. This is how the graph will go. And now marking the points. A, B, C, D. Explain how to determine the pH. Okay, answer these questions. Now, all of you please try to participate. This is exactly same question as we have done earlier. This is the third question I'm doing on the titration curve. So I'm expecting you to answer this. Equivalence point, C. Very good. Very good. And Maximum buffering. Maximum buffering. This is the equivalence point and this is the half equivalence point, this one. So B, best buffer. This is the maximum buffering. pH equals to pKa. Sami, your answers are not coming. pH equals to pKa. B. Atharva, pH equals to pKa. The best buffer area. No. Sanvi, no. A is pure base. This one is A. This one is A, pure base. Right? pH depends on BH plus. Means there is no base, no acid, this BH plus only. Isn't it equivalence point? C. pH depends only on the amount of excess of strong acid. EC, right? pH depends only on BH plus. Because equivalence point when B is 0, acid is 0, both of them are 0, 0. Remember we were doing calculation. And excess of acid is here. Practice these curves, children, and they are very important for your future understanding of organic chemistry, biochemistry. You're going to deal with these titration curves in your colleges also. So that's the end of this unit. Indicators, I think I told you the indicators. Indicators, they show a change in color due to change in pH. Like for example, phenolphthalein. Phenolphthalein is colorless in acidic condition. When the pH is low, it is colorless. But when the pH is very high, it shows the change in color with this range. Means if pH is lesser than this 9 value, it is totally colorless. But when the pH is more than 9 value, when the pH is around 10, 11, 12, then it shows pink color. So generally it is used in the titration of strong acid and strong base. It's always used whenever there is a strong base, it is used. Why? Because in the presence of strong base, after the equivalence point, strong base, after the equivalence point, the pH is going to touch the point 12. pH will go here in between this. If I take a strong base in any of the titration, you can take a weak acid with a strong base or strong acid with a strong base. The presence of strong base will make the pH jump around in between this range. And what's the color in this range? Pink. So phenolphthalein is an indicator which can be used in the titration of a strong acid and strong base or weak acid and strong base. Methyl red, check. When the pH is below this range, below this, then it is red in color. This is red and this is orange. So the color changes from orange to red. Orange to red. But what is needed? pH should be below 4. Who can ensure that the pH is going to be below 4? A strong acid. So whenever you're using a strong acid with strong base or with weak base, the presence of this strong acid, methyl red are the best indicators again. Because strong acid will drop the pH very close in this area. Definitely the color will change as you add one extra drop of acid. So these things I can keep repeating, but you can understand them better if you review the classes and ask questions. Somehow you're not doing that, children. So it's very high time. During this break time, you must review the classes, the recordings. Okay, starting the new topic, Unit 9. That's going to be the last unit. 6 you have already done with me. You can see the presentation? Yeah. Okay. Hmm. So if you remember, the Unit 6 was dealing with thermochemistry. You did cup calorimeter, bomb calorimeter. In the schools, I think nowadays Unit 6 is going on. Jyoti, which unit is going on in your school? Jyoti, Sanvi, and Partha, can you type your units? What are the units going on right now? Atharva? Oh, Unit 4. But whatever unit. Yeah, Jyoti is moving faster. Equilibrium, she is on Unit 7. Atharva, no unit is going on right now. Sammy, what about you? Sanvi, how come your school is so slow? Partha is saying midway through equilibrium. Okay, Partha, you're doing good there in the school? Okay, okay, good. So now this is the last unit. It's going to be very easy, children. Unit 6 we have already done about the thermochemistry, Hess's law, cup calorimeter, bomb calorimeter. It is based on that. Okay, so when I started Unit 6 at that time, I told you that nature likes two things. So basically, in this unit, you are going to understand the stability. We have already done one important thermodynamic quantity, that is delta H. H means heat. Delta H is called as change in, delta means change in enthalpy. What's the meaning of enthalpy? Heat content. That's why the symbol is H. So this we have done in detail, how to calculate delta H experimentally by using cup calorimeter, bomb calorimeter, how to calculate delta H theoretically by using formation enthalpies, by using bond enthalpies, bond energies. So we did plenty of questions, Born-Haber cycle, Hess's law, plenty of things we did. Unit 6, quite lengthy. But here delta H, we are going to deal with this again, but with that, we are going to know two more quantities. One is delta S, which is going to tell you the disorderness, randomness of the system. High energy, low energy, that is delta H. So what nature wants? Nature wants delta S, which is also called as entropy. Nature wants high entropy, high. High means nature wants a positive value for this. More randomness, more is the stability. And this is the second law of thermodynamics. Entropy of the universe is increasing. You know what is the first law of thermodynamics? What is the first law of thermodynamics? Yes, children? Yes, Partha. Energy of the universe is conserved. Very good. We did that cup calorimeter, bomb calorimeter. They were based on this law of conservation of energy. So reaction is losing energy, water system is gaining, and from there we were calculating delta H of the reaction. So that unit 6 was completely based on First law of thermodynamics, that energy can neither be created nor be destroyed. Energy of the universe, not the system, energy of the universe, system and surrounding is conserved, right? But this unit 9 is based on second and third law of thermodynamics, that entropy of the universe is increasing. That's why we say universe is expanding. Why people say universe is expanding? What's the proof? Second law of thermodynamics. It's a law. Law means no arguments. Of course, they have mathematical proof. Everything is there. But we are not learning much in detail. So when people, a scientist tell you this is the law, so we have to accept it as such, right? So of course, if we are on high level, when you go for college and higher studies, there is a proof for everything, right? So entropy of the universe is increasing. If the universe is expanding, expansion means more randomness, more space, then it means entropy is increasing. So increase in entropy is liked by nature. And energy, a decrease in energy is liked by nature, low energy. So delta H, nature wants negative, less. Means nature looking up for exothermic reactions, exo, where the energy of the system is decreasing. Exothermic reaction, unit 6, energy of the system decreases like this. This is the reactant. If it is exothermic, this is the reactant, this is the product. Then if you remember, we discussed the energy profiles, everything. Which one is more stable? The product. The product is more stable and reactant is less stable. So lesser the energy, more is the stability. So we can say that these two factors will control whether the reaction is, whether whatever change is taking place is spontaneous or non-spontaneous. Do you know the meaning of spontaneous and non-spontaneous, children? Meaning of spontaneous and non-spontaneous. Spontaneous, the one the nature is helping them with the help of the external forces of the nature. Yeah, you're not doing anything. Like these boys are skiing and this one is coming down, this one is going up. Which one is spontaneous? A or B? Red or blue? A is more spontaneous. So who is helping A? Why A is spontaneous? Who is helping? Nature. Nature by giving gravitational. Yeah, gravity. Yes, gravity. Children, you're understanding this? So, spontaneous process is sponsored by forces of nature, like gravity. Okay, they are controlled by nature. They can happen on their own. You need not to do anything. You need not to supply energy. But a non-spontaneous process, like the boy is going up, blue boy, continuously he's using his energy to move against the nature, right? To against the gravity. And that is a non-spontaneous process. Okay, so spontaneous and non-spontaneous process. Can we do this question 25 and 26? You put salt in water and don't do anything. Will it dissolve on its own? A pinch of salt in water, will it dissolve? So is it a spontaneous or non-spontaneous? So you are going to answer all these questions and spontaneous and non-spontaneous. If you don't want to type the full letter, full sentence, full word, then put S for spontaneous and put NS for non-spontaneous. But I want answer from all of you. Okay. B part. There is a clear solution, water. You put a drop of ink. Yes, very good. Sammy, try to answer these questions. They are fun. C part. There is iron lying outside for years and years. Very good. Very good. Sammy, you're not there? D part. You clean your bedroom, Sammy. Is it spontaneous, non-spontaneous? Non-spontaneous, because you have to clean it. If you don't clean, it will not get cleaned on your own. 26. A house is built. A house is built. Very good. It's non-spontaneous. You have to make it. A satellite is launched. A satellite is launched. You are working against gravity. A satellite falls back on the earth. Yes. A kitchen gets cluttered. Kitchen gets cluttered. No, 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 no. It's spontaneous, children. Cluttered means entropy is increasing. Do you want to clutter your kitchen? No, no one wants. When I'm working in my kitchen, I just ensure that uh, actually my kitchen is one of the best kitchen around my house, like around in my crowd. I generally ensure that everything is clean and properly placed. I have this habit, but it's very difficult task for me because every time I have to ensure that it should not get cluttered. Every time I have to keep everything at the right place. So when I'm cooking, I'm keeping things at the right place. I'm cleaning them immediately, which is quite tiring, right? So I'm using my energy to make it uncluttered, to ensure that it doesn't get cluttered. If I don't ensure, it will get cluttered. And that's what nature wants, randomness. Because if you try to avoid randomness, children, I'm avoiding randomness in my kitchen. I have to spend my energy and I get tired after working in the kitchen. But if ladies are there, they don't care about the clutterness of the kitchen and they are doing happy cooking because this is what nature wants. They are very happy when they are cooking. I'm also happy, but I try to make myself troubled by ensuring that it should not get cluttered. Okay, so we should work with the nature. So I don't like my habit, but somehow. So I'm trying to reduce my habit of just controlling everything. So if you work with the nature, you'll be more happy. So spontaneous, non-spontaneous, clear? Okay, now this is the last thing which I will do today, thermodynamic and kinetics. You have done kinetics, children, right? Kinetics, rates of the reactions, rate, unit 5, I think is covered in many schools also. Rates, rate laws, catalyst, activation energy, Arrhenius equation, rate constant. So there was an equation which we did in kinetics, Arrhenius equation, that rate constant K is minus EA over RT plus ln K. ln K. ln K is minus E over RT plus ln A. This is the Arrhenius equation. In this, K is the rate constant, E is the activation energy. Like if I make a graph here, like this, reactant, product. What is the activation energy for this reaction? If you remember, it is the minimum amount of energy needed to reach at the top of this hill. This one. We did the Maxwell-Boltzmann distribution curves also. This is the activation energy. If you don't supply this much energy, reactant to the top of the hill. So reaction is reactant to product. If you don't supply this much energy, reaction will not happen. And if I make another graph on the top of this, This one. Now you can see activation energy is more higher. So which one is slow reaction? The one with high activation energy or the low activation energy? It's a very important question and it's free marks. Which one is slow reaction, children? The blue one or the red one? This is red. So which reaction needs more energy to give the product? The blue or red? I hope you are listening. The blue. So which reaction is slow? Which reaction is slow, Partha? The blue, yes. So kinetically, kinetics. Now I'm talking about kinetics. Kinetics means rate, slow, fast. So kinetically, blue reaction is slow. Is kinetically not favored. It's not, kinetics are not playing, kinetically it is controlled. It cannot take place or it needs more energy. But the red one is kinetically faster, right? Now what I'm going to do, I'm just doing some changes here. Sanvi, try to answer. Sanvi and Jyoti. I'm doing the changes. Like this. I'm doing the changes. This is the reactant and this is the product for the red reaction and this is the product for the blue reaction, right? Which product is more stable? The red or the blue? Which product has less energy? Which product has less energy? Blue. So blue is more stable, Sanvi. So now look at this. The blue curve energy profile, the activation energy is very high, but the product is very stable. So the blue one is the one with more stable product. So thermodynamically it is favored, but kinetically it is not favored. The red one is thermodynamically not favored because the red product is less stable, but kinetically it is faster. You can understand the difference. If activation energy, so please write on this. So I'm going to make it very simple. If activation energy EA is less, then reaction is kinetically favored. It is kinetically favored. Right? Give me 1 second, children. 1 second. If activation energy is less, then it is kinetically favored. If activation energy is more, please write on this, then kinetically not favored. Slow reaction. Kinetics are not favorable. Not kinetically not favored. Slow reaction. If the energy of the product's energy is less than reactant energy, if product energy is less than reactant energy, thermodynamically favored. Thermodynamically. So some reactions are thermodynamically favored. Thermodynamically. This is thermodynamically favored. And the reverse, I don't have space to write, so you can write down. If product's energy is more than the reactant energy, then thermodynamically not favored. So in the nature, children, chemicals are lying. They are lying there for years and years. No reaction. Why? Because either the kinetics is not favoring it or thermochemistry is not favoring it. If kinetics is favoring, but thermodynamically reaction is, the product is very high in energy, that reaction will not take place. If thermodynamics are favoring, but kinetics are very, activation energy is very high, that reaction will also not take place. That can lie there for years and years till the time you don't supply a large amount of energy to reach the activation energy. So that's the chemistry, which is very simple, but sometimes many children are very confused with this. So that is the reason I picked up this question, which is going to help you in understanding this concept. So can we answer this question? These are reaction numbers are written. This is the reactant, and these are different products. Reaction number 1, 2, 3, 4, 5. So total 5 reactions are there. Read the question and answer it. Semi, answer the question, children. Which reaction is the fastest? So just check which reaction has the minimum activation energy. You can see the activation energy. Fastest, slow, fast, activation energy. So I think which reaction is the fastest? Activation energy. Athava. Okay, I think he has given all the orders. 5 has the minimum activation energy. Then 5 minimum. Then 1 is equal to 2 is equal to 4. They are of the same activation energy. See here. And then in the slowest reaction is 3. So these are the one with equal rates. Explain why? Because activation energy is same. Sanvi and Jyoti. Clear? Okay. Yes, yes. It is completely based on activation energy. The rates K, you remember I was telling you ln K is minus EA over RT plus ln E. What is K? K is the rate constant, which depends only on activation energy and temperature. Higher the activation energy, lesser the value of K. You're getting it? So K is controlled by, rate constant is controlled by activation energy and temperature. And K, rate constant, is going to determine the rate. Fast and slow. B. Let's do the B. Which one is endothermic? Which one is exothermic? So this is the energy of the reactant. Don't you think that these all are exothermic? So except 4, rest all are exothermic. 4 is above. 4 is above. So except 4, rest all are exothermic. Tanvi, Jyoti, it's very simple. See, put a line here. These are exothermic. The products have less energy than the reactant. This is endothermic. So this question is done. Rank the exothermic reaction from greatest to least. Greatest energy, delta H, maximum delta H. Can you check which one has the maximum delta H? This one. Reaction 5 and 2. And this is reaction 1 and 3. So the greatest is for 5 and 2. And the minimum is for 1 and 3. This question is there on my website also in the quiz. So please ask your questions from this part. thermodynamically and kinetically. Kinetics means high activation energy, low activation energy. For kinetics, you are checking activation energies. For thermodynamic, you are checking the difference in the energy of the product with the reactant. Can you tell me which product is most unstable here? Unstable. Which product? In all these reactions, these are the products. Which one is most unstable? Sanvi? Most unstable product. Mhm. Unstable, Atharva. 4. Unstable means high energy. I'm asking the question unstable. Unstable means, you remember the mantra in chemistry? I'm teaching you from the starting only. High energy means unstable, right? Low energy is stable. So which one is the most stable here? Which product is most stable? 5 and 2. This one with the minimum energy. So this is thermodynamically highly favored. 1 and 2 reactions are thermodynamically very favorable. So this reaction 5 is very lucky. This reaction is kinetically favored and thermodynamically favored. So this reaction 5 is the fastest reaction with the highest amount of energy released. Very spontaneous. Reaction 5 is highly favored kinetically as well as thermodynamically. Okay. So, children, that's the meaning of the spontaneity. That's the meaning of the kinetically controlled and thermodynamically controlled. In the next class, I will teach you about the entropy. The second law of thermodynamics, entropy of the universe is increasing. Hopefully, next class will cover nearly 90% of this unit because it's a 2-hour class. So, I'm planning to finish everything before your breaks are over. If you people are interested, I can arrange a class, extra class, so that you need not to take class on first your 31st of January. So will that be okay if I shift the 31st January class on in between before that? I need only 4 more hours and we are done with this unit. So this Sunday, can I take this Sunday? Okay, thank you very much, children. That's a very good response. So this Sunday, you are on EST, most of you. Am I right? So you'll be traveling. Sunday morning. Partha, Sunday morning you are not traveling. You're on EST, most of you. So I would like to start early. So I'll confirm the time on WhatsApp. So children, any other day, because you are on holidays, yeah, we can do that. Why not? But then any other day, like we can discuss this on the Monday class, right? Your classes are on Monday, correct? So we can discuss it on Monday class. And in the Monday class, I can fix a day during weekdays so that most of you can attend it. Those who are traveling or due to any reason cannot attend, they can watch the video. But children, now I'm after you. I will be chasing you up once we are done with the syllabus. I will be chasing you for the quizzes. Please do not start from 0 unit. Many students, they are going back and starting from 0 unit. Leave it. It's just a mathematical background. You are good in that now. Okay. Now you start with unit 1. Even not with unit 1. You start with unit 9. Once you are done with unit 9, start with it. Unit 9, unit 8, like this. These are the most important units. Okay. So we'll decide the extra class in the next class. And hopefully we are done after 4 hours. Okay, see you then. Bye bye.